with me. It means buckle your seatbelt, Lord, because Kansas is going bye-bye.
not very familiar with how to best way to do the imports here in Rust. I'm not sure. I should ask the LLMs. I wanna capture one file, or maybe just like this. It says it doesn't work.
absolute best way to handle this in Rust is by using generics combined with trait bounds from the popular number trait. Here's how you can set up a generic matrix struct capable of handling any float size. One, add the dependency in the standard library. Traits for mathematical operations, like add, mul, are separated, and things like .ext or .pav only exist on concrete types. The number trait bundles these into a single float trait. Add this to your cargo.toml, meaning TOML dependencies number traits 0.22. Define the generic matrix. You can define your matrix struct using a generic type parameter t. Rust is number underscore traits float derived debug. Float pub struct matrix t pub rows, usize, pub calls, usize, pub data, vet t, and t. Float matrix t create a new matrix filled with zeros, rows, usize, calls, usize. Self t0 comes from the float via zero trait data vet. T0 rows calls matrix rows, calls, data a placeholder for your forward pass layer operation example multiplying by weights pub and simple underscore forward self, weights, matrix t, your matrix multiplication logic here. Because t, float, you can use dash, and methods like .ext toto. 3. Using the matrix with different sizes because this is resolved in compile time. Monomorphization, you get zero cost abstractions. You can instantiate an F32 network or an F64 network whenever you want, and Rust will compile highly optimized machine code for each. Rust main F32 matrix for vent. Low memory experiments with float 32 underscore matrix. Matrix F32 matrix 03. 3 and F64 matrix for hypersync experiments like float 64 underscore matrix. Matrix F64 matrix 03. 3 F32 matrix. F32 underscore matrix for data 0 prequel. F64 matrix. Float 64 underscore matrix. Data 0 minus bridge works best for n experiments activation functions. Because t implements float. You can call mathematical functions directly on your data inside your forward slash active passes. For example, implementing signal. Or no, you become strict. Rust button signal one self like 1 t1 for double self data.
They both want me to use the library there. There's also I think it's like this. I forgot. Or maybe this is the better way to do it. Is using the rows and columns as the index, I think. And then the data is just one giant vector. What creates the illusion of the matrix is the how you access the index. I think that's probably better because of how it's gonna work in memory. But and that this is what I was thinking now. That like these two here are not really. Maybe it would be the full matrix if I did it like this as well. But I think it's different. Because it's different than doing this, right? I think. Not really sure though. This would be only one. So it would be like the axis of the matrix, but it wouldn't be the matrix itself. Unless I use this as the coordinates, but then I need one for the data, so I think the other one makes more sense.
Short and direct answers. One module setup. Best way. src/mural_net/mod.rs/rust.mod matrix src/main.rs/rust.mod mural_net matrix matrix sort. Use mural_net matrix. FN main layout. Matrix F32 matrix new 3. 4. This is the cleanest and most common pattern. 2. Flag vec TBS nested vec vec T your current struct. Rust bug struct matrix T. Float row. Vec T. Left wing arrow this name is confusing column. Vec T. Left wing arrow this is wrong for matrix recommended. Flag vec rust arrived debug. Clone bug struct matrix T. Float data. Vec T. All elements in one contiguous vector rows. View size. Calls. View size. Right flag vec is better. Much better. Performance. Contiguous memory record arrow better cache. SIMD friendly. Easier/faster matrix operations. Lower memory overhead standard in all series ML libraries. End array. Fair. TCH. Etc. Nested vec vec T is slower. Uses more memory. And is painful for linear algebra. Quick fix for your file. Replace your struct with the flat version I showed above. And I'll help you fill in the block next if you want.
I think that makes more sense. Just gonna use this. What is this? Yes.
Disables any electrical system in the blast radius. It's the only weapon we have against the machine. Solar systems used to be cities that spanned hundreds of miles. Now these cities are all that's left of them. Quiet. We got trouble.
Also uses use, not mod. I was there or I was doing that before.
Tank, load the jump rope.
You have to let it all go. Fear, doubt,
So the first thing that I need to do is to clarify the I/O. This one I got from an implementation that I saw from Micrograd. Initially I was trying to convert Micrograd, but then as I was trying to convert, it was annoying me how confusing it was. And I really didn't like it because of that. There was a bunch of different parts that were confusing me. I was trying to convert from Python to Rust. The first time that I tried to convert, I did it on stream. Then after that, I looked into the existing implementations because I realized that I didn't have the dataset. Because on the Python version, he creates using sklearn, I think is the name of the library to generate the datasets. So I got this function from one of the implementations that I found. But then the most recent time, which was yesterday, I was trying to convert again. I stopped midway through because it was annoying me how like it seemed very inefficient. And I think he did it like this because for teaching, but it was annoying me, and I was a lot more curious about my own ideas that I was having, that I was trying to think about like how to do it differently. That's basically what I'm trying to do now. Paste this. I think this is one just pasted. Yeah, here's the main. I think I'm gonna go over the Micrograd thing that I was trying to do there and explain how I think it works. And spend some time discussing the implementation with ChatGPT. It's not very clear to me. It's not very clear. Like there's something there, but I'm not really sure. It's not very clear on my mind the actual source. One of the main sources of confusion is that he uses the value class for everything, and that was confusing me because I wasn't being able to I forgot that the weights were actual value classes as well. The memory thing was the thing that was most confusing to me, and the backwards function. But the way that I was thinking is that there is a relationship between the way that he did the backwards function, where he defined the function inside of another function, and the memory. And that relationship is very confusing and very hard to understand. And I think that the fact that he did it the way that he did, and the way that I naturally, like there's a difference between the way that I was naturally thinking about and the way that he did. And I think that difference is anchored around how the backwards and forwards propagation works. So that's one of the things that I'm trying to see if I can clarify here. I need to, first I need to understand the boundaries here, like the inputs and outputs. Because this is another part that has always been very confusing to me. It's like, how do you define what you stand as inputs? Like how many nodes you're gonna have on the inputs? How that's gonna relate to the first layer, to the size of the first layer, and then how many outputs you have as well. And what exactly is the network trying to do? That was like, it still is something that is kind of confusing to me, because there's a lot of different assumptions and things. But I think in essence, what the network is trying to do is trying to capture a functional behavior of inputs and outputs. So it's like you're using data to recreate a function organically instead of hard coding. Basically what is going on.
Seems that you've been living two lives.
I think on this case here, I'm gonna have to use another one because this one. On this case, I think that if the function there that builds the dataset is basically what we're trying to reconstruct, but from the neural network instead. So you just get the inputs of the function, and then you train the neural network to basically have the same behavior of the function, but organically, instead of hard coding the function. I already ran this once, then it basically creates this image based on the visualization creates the image. I think the generate moon creates the points on the image. I think what the neural network has to do is to create a line that separates both of them, probably.
You ever have that feeling where you're not sure if you're awake or still dreaming? It's called mescaline. It's the only way
I'm gonna open the micrograd implementation to talk about. I can clarify. I know I have like a decent idea of the direction that I'm trying to go here, but the reason why is still kind of unclear to me, because the micrograd implementation is still kind of confusing to me when it comes to the memory. I was trying to convert here, like one-on-one conversion. The problem is the way that he does the backwards here. And also the way that it works in memory. So that's the thing that I think is most confusing. But basically the value object is the thing that encodes the state of the calculation. So that's one of the things that was confusing. But the data here, in the case of when you use the value to initialize the weight values, the data is going to be the actual weight. So like a small thing that was confusing me. And then the other thing is how the memory is going to work between the forwards and backwards pass. It basically builds this, which is a class that has function embedded into it. So each value is like a functional thing that holds state. So the state is going to be the value of the network. And this is like a node in the layer, I think. Then from this, it uses this to create the neuron, which is basically this array of values, and the bias. So this allows it to create the calculation of the activation of the neural network. Just the multiplication of the inputs, which is x, times the weight. So zipping is going to loop on both of these things at the same time. So for each input that you pass here, it multiplies against the weight, and then it sums with the bias in the end. And then it calls value, because this is the part that I think it was the most confusing. That when you multiply these two here, what's actually happening, because both of these things are value objects, value classes, it's gonna call this function here, and then this function is gonna return a new node. But then I was confused about what does that mean. And I think that according to ChatGPT, and I kind of agree now, but I'm still kind of confusing, I don't think it's gonna change the initial value here. So these weights are always going to be the same. Yeah, but this is the part that is still kind of confusing. Because I think when he returns the value there, it's not changing the weights that are actually here. That makes sense. But it doesn't matter, I think, because it's gonna update the weights based on the learning rate. Yeah, so I think that this is what's going on. So it only initializes the neural once, the lifetime. So this creates basically a layer, I think. Or maybe not, actually. But I think this just creates like a DAG, a computational. Yeah, but it would be like a... It's one neuron on the layer. But the array of weights kind of represents the neurons on the previous layer or the inputs in the very beginning. Yeah, so this is what's going on. So like the size of this thing here is gonna be directly correlated with the inputs from the previous layer. So it's kind of creating the edges from the previous layer to this node. So this would be like one node on the network. And then uses this one to create a layer. So this is going to be the size of the layer of each layer. And then the entire network is obviously going to have a bunch of layers, which is based on the inputs and outputs. So this is the number of inputs you have, number of outputs you have. It creates this, and then it loops over to create the amount of layers it's going to have based on this. So the details don't matter that much here. It's basically creating a bunch of layers based on inputs and outputs. Then each one of the layers creates a neuron, and each one of the neuron has this encoding of the mathematical equation, which is inside of the value. So it creates this only once for each layer. So the weights are only random in the beginning, I think. But then during the calculation here, the values don't change. It's during the loop of the loss that is gonna update the values of the weights. So here's the example that he has. The grades based on 2 layers, 3 outputs, I think. Yeah. Whatever. And this is the loss function. This is another part that is kind of confusing. I don't know. I'm not very sure what the map does here. But I think it's just creating like key value pairs. I think, maybe. Or like it's transforming each value of the row into a value. So these ones come from the... So you see, he is using sklearn to generate, but it's basically very similar, probably. Just an equation that creates this graph here. It creates 2 different types of points, and I think that what the network has to do is to create a line between them. I think that's what is going on. So the inputs are gonna be the points, I think. Both either blue or like all the blues and all the red points. That's basically what this is, I think. Yeah, so X and Y. It's gonna feed this here. So it uses this XB, so I think that's it's only one type of dots there that is gonna feed the neural network. But I think that's, yeah, this is what's doing the testing, I think. So like the activation, the forward pass, which is just based on this XB here. And then based on the scores, it's gonna calculate the loss, which is the delta, I think, from what it was supposed to be and what it got. I guess it makes it slightly more confusing because I don't know, like I'm not very confident on how does the map work here. Like it doesn't make a lot of sense to me, not very intuitive. But I also don't care that much about this. And then the training loop is gonna be here, and that's where it's gonna change the. So this is the part that was confusing because here it says data, but the parameters are actually the weights on the. Not really. I think it's just the weights. So it gets the parameters from the layer, gets from the neurons, and the neurons. Yes, it's the weights and the bias. So it does update the bias as well. So it does the forward pass, which does a mathematical calculation for each of the nodes, and then through the mathematical calculation of the forward pass, is gonna capture the state on the backwards here. Actually, it doesn't call. This is the part that is weird, because there's nothing about this function that says you need to define inside of the other function. So this is bad, but he did it like this for educational purposes, and this is one of the things that was annoying me. The purpose of this is to capture the data, and the purpose of the backwards, what the backward needs to know is what happens before. And this is the thing that is like, this is the, I think, core of the thing that I'm trying to clarify more, because the fact that he used the value class here for all the components of the mathematical equation means that you're gonna need to have a way to differentiate between them, because what matters is the traversal on the graph. Because when you're going backwards, what you're doing is just the chain rule, which is basically taking the local derivative relative to the massive equation you have, and then you are chaining that, so you're summing the results as you go backwards through the graph. And that's what happens here. And the difference is going to be on the way that you derive the operation. So for when you're adding two nodes, I think, yeah, when you're adding two value classes, you're going to sum the gradient of the current one with the output of the sum, of the gradient of the sum. But when you're multiplying, you're going to multiply the data of the other with the gradient of the outputs. So that's the main distinction. So depending on the type of operation that happened to create the node is what's gonna determine what happens on the backward pass. And that's the thing that I'm trying to, I think, see the relationship. So in my mind, I think that I was picking it up like subconsciously, is that the fact that the value class, using the value class to determine all the values of the equation inherently means that you need to capture the state of what created the node, basically, inside of the class itself. And I think that this is probably not the best way to do it. I think it's looking at it backwards. But then at the same time, I think that because as I was talking to ChatGPT, he said that like He said that I wanted to say that I wanted a unique class for each type of value, but I don't think that's probably the best idea either. Like to have one type for the weight value, another type for the bias, another type for the data. I don't think that makes sense. So in my mind, I think what makes more sense is to have only one class and then encode what has to happen during the traversal based on the actual relationship, based on the actual equation, based on the actual equation that is happening. And that's what has to, like, it makes a lot more sense. I'm still confused about the details. That's the part that is kind of hard to me still. Because there's also optimizations here that he only did like small optimizations, but obviously on the bigger libraries they're gonna have a bunch of optimizations. But I'm just trying to like follow from scratch to clarify in my mind how everything works. So I think that this is the key problem. So yeah, what matters is you have a symmetry between the forward and backward pass, and the symmetry is encoded by the gradient. So the backward pass is like the gradient of change of the forward pass, and they are symmetrical. And what's happening during the training process is that you are capturing the latent state based on data. You're trying to capture what is the functional relationship on the data set based on the reference frame of a value, of the target value you're trying to capture. I guess this is the other thing that is confusing to me, which is about the output. Because if you think about it, like what is really the advantage of doing the... What's the advantage of training the neural network instead of just getting the function? And the obvious advantage is for the cases where you don't know the relationship. So instead of deriving yourself, you try to capture based on the data. But then this is the thing that's the reason why it's so confusing to me about the output. Because inherently that's a double-edged sword, because it's like the correlation doesn't mean causation type of situation, where like can you train any neural network to capture relationship on any data? What makes it the data? What makes it what about the data? What is about data that allows you to train the neural network in the first place? What does it say about the data? And like, how do you know? Because you're essentially projecting your worldview, because you are making assumptions about the data, and then that's clouding how you are structuring the thing in the first place. That's why I think that the inputs and outputs are very hard to understand.
Works for easy data sets, but moons look more like XXXXX with boundaries as a curve. That is why hidden layers are needed. What does the network architecture look X, Y16 neurons, 16 neurons. 4. What shape should your matrix have? If you make a dense layer, 2 inputs, 16 outputs, the weight matrix is 16 times 2 because each of the 16 neurons receives both inputs. For example, input X, Y cubed, output W input beware. W 16 times 2 input 2 times 1 output 16 times 1 a concrete example suppose. Input point, 0.8, 0.3 belongs to class, 1 forward pass, 0.8, 0.3 downward arrow against 2 rightward arrow, 1 6 downward arrow, 10 downward arrow against 1 6 rightward arrow, 1 6 downward arrow, 10 downward arrow against 1 6 rightward arrow, 1 downward arrow, 0.73 prediction, 0.730 therefore, predict class 1 if the true label is 1 the error is small. The decision boundary visualization the code you already have is preparing for this. For every pixel in the grid, rust left 0, left 0, you eventually want rust with prediction modeled up forward back. X 0, Y 0 then, rust if prediction 0.0 color red else color blue. This paints the entire plane according to what the network thinks. After training, you'll see a curved red slash blue separation line wrapping around the moves. So the simplest first network for your data set is inputs, 2 hidden, 8 or 16 hidden, 8 or 16 outputs, 1 with training examples, rust x spec, x underscore cooler, y underscore cooler by 1.0 or minus 1.0 and the output interpreted is rust prediction 0.0 class 1 prediction 0. 0 class minus 1 that's essentially the exact task Carpathy uses in the micrograd demo. Learn a nonlinear decision boundary that separates the two interlocking moons.
The other thing that is making it confusing for me is the distinction between the training parts of the equation and like actually using the training and the inference is kind of confusing to me. I think I have to clarify this more before I try to do anything. It's still very confusing to me. The problem is that, like, if I ask the difference about the training and inference, it's just gonna give me like shitty response. I think that's not exactly what I want to know. I already obviously understand that when you're training, you're basically trying to calculate the weights. They're basically building a mathematical equation based on the data you put, and then you use the loss function as a reference frame to generate the gravity, the direction of the gravity of the weights, so that you capture the latent state.
Do you want to know what it is? Remember, all I'm offering is the truth, nothing more.
What is real? How do you define dreaming? If you're talking about what you can feel, what you can smell, taste, and see, then real is simply electrical signals interpreted by your brain.
You're extremely close. The thing that's tripping you up is that you're thinking about the data set variables, x and y, as if they were networks input/output dimensions. They are. Let's inspect what your generator actually returns. The function returns rust vec64, vec64 zone, rust lex, y generate underscore means. Means, rust x vec64, y vec64 for example, with 3 samples, rust x vec, 0.7, 0.8 vec, 1.2, minus 0.3 vec, 0.9, 0.9, y vec, 1.0-1.0, 1.0, notice, rust x 0 vec, 0.7, 0.8 y 0, 1.0 these belong together. This is one training example. Input 0.7, 0.8 target 1.0 another, input 1.2, minus 0.3 target minus 1.0 how many inputs? Each sample is, rust vec, x underscore foo, y underscore foo which contains 2 numbers. Therefore, 2 input neurons, not 1. Your network would look like 2, 16, 16, 1 to 2 comes from rust x 0 x 1 what happens during training? Suppose you pick one sample, rust input vec, 0.7, 0.8 target 1.0 fit into the network, 0.7, 0.8 downward arrow 2, 16, 16, 1 downward arrow prediction 0.34 the network says 0. 34 but the correct answer is 1.0 so there is error. Loss function for a first implementation, MS is perfectly fine. You compute, for this example, 0.34 to 1.0 to 0.4356 that's the loss. Then comes backpropagation, backprop answers, which weights cause this error. And find how much should each weight change. Every weight gets a gradient, loss weight then, learning underscore rate gradient for every weight in the network. What are you actually trying to learn? This is the key intuition. You are trying to learn a function, fxy such that, fxy1, for points on one moon and fxy minus 1 for points on another moon. The network is basically learning, x coordinate, y coordinate, downward arrow, some complicated equation, downward arrow, score where, score 0 moon is score 0 moon b, but you happen to have to train it. Initially predictions might look like 0.12-0.040.3, 0.21-0.09 most random. After training, 0.98-0.920.87, 0.95-0.99 much closer to targets. How do you know it's working? Simplest metric, rust let directed prediction 0.0, 1.0 else minus 1.0 compared with target. Rust with direct target number underscore direct 1 then. Rust accuracy number underscore direct task 64 total underscore samples is 64 for example. 50 random guessing 70 learning something 90 very good 95 excellent for the moon's data set. What should inverse look like? After training, rust with point vec, 0.8, 0. 6 with prediction network forward point suppose. Prediction 0.91 then. Class 1 more. Prediction minus 0.73 then. Class minus 1 no target is needed during inference. Inference is just input downward arrow network downward arrow prediction. What is the result of training? The result is not a 5. The result is train weights for example layer might start as 0.23-0.541.10.04. After training 1.92-2.17.63-1.41. The weights now encode the decision boundary. Shaping a model simply means writing all those learned weights and biases to disk. Something as simple as rust struct layer weights. vec-64 biases. vec-64 serialized to JSONs enough for first implementation. If you're building this completely from scratch, I recommend implementing exactly this order. Matrix multiplication dense layer. WXP. 10 activation forward pass only MSE loss manual backdrop for 1 layer backdrop for multiple layers training loop decision boundary visualization once you can train 2 regular arrow 16 regular arrow 16 regular arrow 1 network on moons and get 90% plus accuracy. You have reproduced them. More mechanism behind modern neural networks yourself. Everything else CNNs, transformers, diffusion models is built on the same fundamental loop. Input downward arrow forward pass downward arrow prediction downward arrow loss downward arrow backdrop downward arrow update weights downward arrow repeat.
if I can do this or not. I also think the vect is gonna be on the heap, so I don't need to return a reference, but I'm not really sure. Because if I can't do this, then I can create a variable. But I think that if I create a variable, it's gonna complain. Sure. Also don't know how to initialize here. Do I initialize a vector? Maybe it's just vec. Okay. Yeah, yeah.
Yes, that's much closer to the right mental model. The one thing I adjust is what constitutes a single input and output. Your network is not learning. Rust vec-f64. Vec-f64, that's the entire data set. Instead it's learning. Rust vec-f64. F64 for one sample at a time. More specifically, Rust x underscore coordinate, y underscore coordinate, class underscore score. So mathematically, f, r superscript 2, r the data set is just many examples of this function. Think about what your data set contains. Rust x 0.7, 0.8, 1.2, minus 0.3, 0.1, 0.9, y 1.0 dash 1.0, comma 1.0. This really means f 0.7, 0.8, 1.0, f 1.2 dash 0.3 dash 1.0, f 0.1, 0.9, y. 0 the network is trying to find a single function that satisfies all of these examples simultaneously. A useful way to think about training is Rust puppet train examples. Vec-f64, f64. Neural network. Notice the output is not another vector. The output is Rust neural network, or equivalently, Rust learn function, because after training you constructed a function. Then later, Rust prediction network to forward vec. 0.5, 0.7 produces Rust 0.92 your statement. The neural network is basically a function that tries to approximate another function based on the data that is being used to train it. Is essentially the core idea of supervised learning. You can think of it as unknown function, downward arrow generate data, downward arrow xy examples, downward arrow neural network, downward arrow approximate function. The Moon's data set is actually a useful example because there really is an underlying rule. Your generator creates Rust x1 cos angle y1 sin angle for one class, and Rust x2 1.0 cos angle y2 0.25 sin angle for the other class. So there is a hidden mathematical process generating the labels. The network never sees those equations. It only sees point A, class 1 point B, class dash 1 point C, class 1, and must infer the pattern. This is why people often describe machine learning as function approximation for examples. You don't provide Rust if points underscores underscore and underscore for underscore we return 1.0 else return 1. 0 instead you provide examples and say, figure out the rule. The weights become compressed representation underlying underscore rule input even though the network never explicitly learned the original equations. One subtle but important point, the network is usually not reconstructing the exact generating function, it's reconstructing a function that behaves similarly on the data distribution. For example, your mean generator uses trigonometric equations. A neural network will almost certainly not discover rust, cos, sin internally. Instead it will discover some complicated composition of weighted sums and nonlinear activations that produces roughly the same classifications. So the goal is usually same behavior, not same formula. A useful abstraction is Rust struct neural network parameters. WebF64. Training is reading. Find parameter values such that network X for many examples. That's the whole game. The architecture tells you what family of functions is available. The weights select one specific function from that family. The training process searches for the weight values that best explain the observed data.
So basically, that's the whole thing that I was thinking about, or I was talking about the outputs and inputs before, is that we're basically reconstructing the function from the data. And that's why it's always a double-edged sword, because by definition there's going to be an infinite amount of different rows that satisfy the certain thing you're trying to recapture from. We're basically using the data to create a row by training the neural network to capture that relationship. But in the process of training the neural network, because there's an infinite amount of relationships you can get from the data, you're never really going to be able to know if the thing that the neural network is capturing is the actual relationship or not. And obviously, the bigger the network, the bigger the emergent patterns you're going to have. So it becomes, as the network scales, it becomes more non-deterministic, because the complexity of what you're trying to, the relationships you're trying to capture becomes bigger. It's still kind of hard for me to understand what does it mean to feed the inputs into the network. That's the thing that I'm trying to clarify now in my mind. Because here, so if I understand correctly, what the function returns is going to be this vector, which are basically the points on the graph. Is the coordinates of each point in the graph. And I think the y is the expected one. I'm not really sure. I think that the x is the inputs and the y is supposed to be the output. So we use the coordinates to capture this, but I don't, not really sure if I understand that correctly. The class score. It's basically a function that, when accepting this, has to return this. And this would be like the correct response the network is supposed to capture. Be right back.
I think you are making one architectural mistake that's causing most of the confusion. The neural network is not a matrix. A neural network contains matrices. Something more like Rust struct neural network layer 1, matrix F64, layer 2, matrix F64, layer 3, matrix F64, or even Rust struct dense layer weights, matrix F64, biases, vec F64, struct neural network layers, vec dense here. That mental shift makes everything much clearer. One, should I split train/test? Absolutely. For example, 100 samples 80 training 20 testing training, used to update weights testing, never shown during training after training. Rust lit prediction network the forward test underscore input compare against. Rust test underscore target. This tells you whether the network actually learned the pattern or merely memorized the training examples. 2. What does feeding data into the network mean? Let's take one sample. Rust let sample vec 0.7, 0.8. Remember, 2 inputs. Suppose the first layer is 2. 16. The weights are 16x2 conceptually, x1, x2, and 1w, 11w, 12, and 2w, 21w, 22, and 16w, 161w, 162. When you feed the sample 0.7, 0.8 into the layer, you're computing wxb. The result is 0.34 minus 0.12, 0.91, which contains 16 values. That's the activation of the hidden layer. Then 2, 16 becomes 16, 16, and then 16, 1 until finally output 0.87. So feeding input simply means Rust late output layer to forward input where internally you are doing matrix multiplication. 3. What should train return? Not Rust vec F64. This is where your design is going wrong. Training does not produce predictions. Training modifies weights. So I'd think about Rust pub train mud self x vec F64y F64. Notice Rust mud self the network itself changes. The weights get updated. After training, Rust network forward will behave differently because the weights have changed. For what is the actual output of training? Suppose initially layer 1 weights 0.13-0.420.81. After training 1.91-2.040.55. Those new values are the learned model. Training's job is random weights downward arrow gradient descent downward arrow useful weights 5. How do you use the network later? After training, Rust lit prediction network forward vec 0.5, 0.8 maybe, 0.93 which means class 1 or minus 0.87 which means class minus 1 that's inference. 6 should I save weights? Eventually yes. But don't worry about that yet. First get training working. Later, Rust struct dense layer weights, vec f64, biases, vec f64, can be serialized to JSON. Something like JSON weights, biases, is enough. Loading the JSON recreates the trained network. 7 what would I build first? Honestly I'd start much simpler than a full multilayer network. Build a single neuron. 2 inputs downward arrow 1 neuron downward arrow 1 output something like Rust struct neuron weights, vec f64, bias, f64, forward pass, Rust pub forward self input, f64, f64 self weights 0 input 0 self weights 1 input 1 self bias train it. Watch loss decrease. Then build 2, 4, 1 then 2, 16, 16, 1 8. What should your architecture roughly look like? I'd separate concerns. Rust struct matrix T data, vec T, rows, usize, calls, usize, only responsible for matrix math Rust struct dense layer weights, matrix f64, biases, vec f64, responsible for WXB Rust struct neural network layers, vec dense here, responsible for forward pass backdrop training prediction then your API becomes Rust limit network neural network new. 2,16,16,1 network train train underscore x train underscore y 1000 lit prediction network forward vec 0.4 0.7 this is much closer to how neural networks are structured conceptually. The matrix is just a low level math tool. The network is the thing that learns. The result of training is simply that the matrices inside the network now contain weight values that encode the decision boundary separating the two moons.
I'm not sure if ChatGPT is right or not. This is something that is confusing me as well. Because on the, like when you think about the DAG, the directed acyclic graph of the computation, you usually think about only once, of it only existing once. But for each node that is part of the layer, it's as if you are using all the other nodes. That's the part that is confusing. So you're doing like a bunch of different DAGs inside of one main DAG, which would be the entire network. Like each node contains its own directed acyclic graph. That's the part that is confusing. So on the micrograph there, the neuron itself contains the computational graph, which is the weights, the bias, and then it receives the inputs. The inputs are the data from the previous layer, I think. Because this is the part that I have to clarify. Which is the most confusing part, is like how does, on the forward pass you are returning new nodes as a result of the calculations from the other ones. But then what does that mean? On the bigger loop, like what happens? Where are these new nodes in memory for the backward pass? Are they the same thing as the neuron? So for each neuron, you're basically updating the value. That's the part that is confusing. So if the model is only initialized once, it means that it's gonna be the same thing. The weights are only random in the beginning, obviously, and then it updates the values based on the loss that it gets here. based on the gradient parameters. So it does the backwards on the loss. The node that it returns from here. So the other one is accuracy. Data loss plus background loss. This is just like more fancy way to do the loss, probably like a small optimization. The idea is basically the same. This is the part that is confusing to me. Because what is going on here on the memory? I think that's like the reg loss that it returns there is not the same as the weight of the model. Like the weights remain the same, but then since they return a new node which contains the whole graph. I think that's the part that is confusing, because it does all the calculations, and then through these calculations the multiplication that is happening here is basically this function, and then each time it returns a new thing here, a new node. So the array that it creates here is basically an array of new nodes through this loop here. Then it does the sum, which is going to be like this function here, which returns a new node. And then this final node that it returns, I think it has like all the rest of the entire graph on it. And that's why it's able to call backwards on that node, and then it's going to call the correct backward function for each one. Because the gradient is encoded on the definition of the function here, which is the part that is confusing and very weird, that I don't like. So the thing that I'm contemplating here is because ChatGPT said that it's not one matrix, it's multiple different matrix. And I think the reason why he's saying this is exactly because of the stuff that I'm saying now, which is not each node is like has an entire computational graph inside of it. It's kind of, you have two different levels of graphs basically happening at the same time. One level is at the value, which builds the mathematical equation. Like this value is the thing that is used to build the mathematical equation inside of the neuron here. Like this stuff here is a graph on itself, is a DAG on itself. And then each one of the neurons has a DAG, so that the bigger graph is a DAG of DAGs. That's the thing that is confusing. I think that the ChatGPT is saying that I should have multiple matrices because of that. But then the question is relative to memory, I think, because the only thing that the reason why it would matter only is because of memory. Because then each thing would allow you to encode different relationships. Because if you only use one matrix, you're gonna update it, you're gonna overwrite the values of the weights on the backwards pass. And you don't want to do that, you want to accumulate. That's what's going on, but I'm thinking about whether or not, like, is this necessarily fundamentally true or not? That's the thing that I'm thinking about now. And the thing, like, is very confusing as well, the inputs is still, because I think it depends on the... I'm trying to think on like a more generic standpoint, not just this specific case. Like I want to understand fundamentally, like, how does it work? The bridge between the inputs and the actual layers. And obviously, I think by now I understand that the network itself is going to be like a mathematical equation. And then the graph encodes the memory state of the mathematical equation. So you're basically using memory to encode the state of the equation. So the values are relative to the density of the data, relative to the loss function, which is based on the target that you're using to train the network. So the gradient is basically updating the variables inside of the function to capture the state you're looking for. It's basically doing a derivation using the data. But because obviously there could be an infinite variance of kinds of input shapes that you can get. Like, how do you structure the network so that it's capable of building the mathematical equation regardless of the shape of the input? That's the thing that I'm trying to clarify, but it's very hard to try to think about, like, how to ask ChatGPT in a way that's not gonna be like, one thing that I'm sensing a lot when I use ChatGPT is that it makes me deviate. It's not very good, like, because it starts to extrapolate in the wrong direction. That's the problem.
After this, they listen to it. Check the clip and story and
Maybe I should ask about the relationship here on micrograph first, because I don't understand this map thing. I have to clarify what is happening here, how it is fitting the inputs into the model. I think it's probably this complicated thing here, which I also don't like very much. But if it is this thing, it's still kind of weird. And so it's recreating each time. That makes it more confusing. Because if it is... No, but the model is only created once. That's the thing. He recreates the inputs here, which I think is kind of bad as well. Like, that's probably why he's using... Not really sure if he's using here. But on the Rust one, he uses a seed, which basically guarantees, I think, that the next time that you use it is going to be the same random distribution. I think that's why he uses a seed. But I don't understand why not initialize outside of the function and then pass as an argument. Maybe it has to be different each time. That's what this permutation is doing. Like, it's getting at different parts of the data sets. It's dividing based on batches. Unless you don't pass anything, then it just gets the whole thing. Yeah, so I think it does create only once, unless you pass the batches thing there, and that's why. But yeah, it is creating only once. And then on this, which is the case that I'm looking at, is gonna be just the input, but the other case is if you want to train by batches. So it's gonna get a random sample from the whole thing based on the batch size. You now understand. So the thing is always the same, the model is always the same, so the weights are only random initially. But then I imagine that this... Actually, I'm not really sure if it is... Because it should be calling init only once, so you should be... I think the map does this here. It calls this thing here. Which is gonna call the call for the layer, which is gonna call for the neuron, which is gonna do the calculation for each neuron. The computational graph. And calculates the value based on that. Like this node that it builds here, I think is gonna be like this out here because it's the result of the bias. Where does it do the topological thing there? Where does it build the graph? Getting sign here. And maybe on the video is different. I remember he did a topological storage thing to create the children. Not really sure how it works here. 'Cause the only way that the backwards work is by. Well, actually, maybe not. Let's see. Also, yeah, it's just here. Inside of the backward function. But then how does it populate the previous here? The second argument to the value. Yeah. Just passing this. So I don't understand why. Or maybe it builds inside of the function there, the backwards function. It builds here. But it's very confusing still. Because you're gonna call this function from the result of all the other calculations. But I don't understand how the final node there. Like, it's not possible for the final node to know about all the other nodes. That's the part that I don't understand. How does it know?
World as it was at the end of the 20th century. It exists now only as part of a neural interactive simulation.
Also, it's capturing based on the parameters, so it doesn't do the backwards on the whole thing. But it's still very confusing to me. I think that this backwards here is not gonna be the main one there, maybe? It's gonna be the one that is created inside of the function. So this is the part that I mean that is very confusing. It doesn't feel right, the implementation. It feels that there's something fundamentally wrong about it, and that's the reason why it's so confusing. But obviously he did this for educational purposes. That makes sense. So I think I understand. So the question is how to create a matrix that is gonna be able to capture the relationship between the pair of values that is receiving with the output that it should receive. That's the thing. So one thing that I just thought about now is why not do the other way around? Why not start from the data? I wonder if that's the same thing. Like instead of trying to use the inputs, you use the output as the input. So you basically invert. I wonder if that's gonna give you the same pattern. Probably would, because it's the same relationship. Not really sure.
This is one of the most important concepts in neural networks. The short answer is, the architecture is usually shaped by the input and output dimensions, but the hidden layers are your design choice. Let's forget neural networks for a moment. Suppose you write a normal Rust function, Rust mat f64, f64, f64 the signature is, f64, f64, f64 the input shape and output shape are fixed. A neural network is similar, R superscript 2, R means, x1, x2, y your data set has exactly this shape. Input shape determines input layer size your samples look like, Rust spec, 0.3, 0.92 values. Therefore, input layer 2 neurons because each neuron receives one input feature. x1, x2 if your data set were, Rust spec, height, weight, age then, input layer 3 neurons if your data set were images, 28 times 28 pixels then, 784 inputs, or a convolutional architecture. So the input layer is dictated by the data. Output shape determines output layer size. Suppose we're predicting a single number. House price then. Output layer 1 neuron. Suppose we're classifying cat dog for 3 classes. Then often output layer 3 neurons example 0.01, 0.97, 0.02 meaning 1 cat 97 dog 2 birds. So output shape is dictated by the problem. Hidden layers are your choice. This part is what the network is free to use for representation. 4 moons, 2, 8, 1 could work. 4, 2, 16, 16, 1 more, 2, 100, 100, 100, 1 all have the same. Input shape 2, output shape 1 but different internal capacity. Why hidden layers can have arbitrary sizes? Think of them as temporary working memory. Suppose 2, 16, 16, 1 input x, y gets transformed into 16 numbers then, 16 numbers then, 1 number. Those intermediate vectors are internal representations. Nobody outside the network sees them. Can a network accept any input shape? Generally, no. A trained network has a fixed shape. For example, 2, 16, 16, 1 expects, Rust spec, x1, x2 if you pass, Rust spec, x1, x2, x3 there isn't even a matching weight matrix. The dimensions don't line up. A matrix multiplication requires dimensions to match. 16 times 2 times 2 times 1, 16 times 1 but 16 times 2 times 3 times 1 is invalid. Then why do transformers seem to accept arbitrary input sizes? Because they're designed differently. A transformer might accept 10 tokens, 100 tokens, 1000 tokens, but each token has a fixed embedding dimension, 768 or 4096 internally. The architecture is built to process sequences of varying length. That's a special design choice. For your implementation, I'd think of your network as implementing a mathematical function, f, r superscript 2, r because, input, x underscore coordinate, y underscore coordinate, output class score. The architecture, 2, 16, 16, 1 is simply one possible way to represent functions of that type. A useful mental model is, input shape downward arrow determines first layer, output shape downward arrow determines last layer, hidden layers downward arrow determine expressive power. So for your moves dataset, input shape 2, output shape 1 possible network 2, 16, 16, 1 the 2 and 1 are forced by the problem. The 16 and 16 are your design decisions.
And so basically what I'm thinking is what I said there is that like the forward and backward pass are symmetrical things. The backwards is the gradient descent, like the delta. The rate of the backwards encodes the rate of change. So there's a symmetry between the forwards and pass and backwards pass. And that's the frequency of that symmetry encodes the topology of the space. Because you have the inputs and outputs, that's a functor, and the pathway between them is going to be a function. And what the neural network is trying to do is update the weights based on that traversal. Like the forwards and backwards pass is like a wave going back and forth between the inputs and outputs to create an image, a high dimensional image or multi-dimensional image of the topology between the shapes of the input and the output. I think the forward pass kind of calculates the friction of the... At first it's going to be random, obviously, because the weights are random. I think that's what the mathematical calculation... You need a reference frame. That's why I think like it is a symmetry, because it's the same with perception, I think. Yeah, it's basically the same thing as perception. It's a self-filling feedback loop system. Because the reference frame is going to be based on the target. So you're projecting your worldview into the map. Because you are the one that selects what you perceive to be good and what you perceive to be bad, based on the meaning you give to the data you're using the network to train. That's the reference frame of the network. Then the loss function is just the rate, the frequency of the symmetrical relationship between the forward and backwards pass. Like the backwards encodes movement. Both of them encode movement.
How to implement multiplication for your matrix type. Rust pub struct matrix t data. Vec t, rows, usize, calls, usize. You'll probably want rust pub self, row, usize, col, usize, t self dot data row self dot calls col then multiplication. Rust pub mat self, other, matrix t assert underscore eq, self dot calls, other dot rows let much result matrix new self dot rows, other. Calls fortune 0 self dot rows fortune 0 other dot calls let some t0 fortune 0 self dot calls some self dot get I, k other dot get k, j result dot data I result dot calls j sum result. That's the canonical implementation. What the network is learning geometrically suppose initially. W 0.1, 0.2 to 0.4, 0.8, 0.7 minus 0.3. These rows define 3 directions in input space. During training, forward downward arrow loss downward arrow gradient downward arrow update weights those directions rotate and stretch. Eventually, W 2.1 minus 1.7 to 0.3, 3.4, 1.9, 0.8. The projections now align with meaningful structures in the data. Your topology intuition, you said. I'm thinking of the matrix weights as encoding the multidimensional space topology of the relationship between the IO topology. That's not a bad mental model. Another way to phrase it, the network defines a sequence of coordinate transformations. Input, R superscript 2 first layer, R superscript 2 rightward arrow, R superscript 1 second layer, R superscript 1 rightward arrow, R superscript 1 output, R superscript 1 rightward arrow, R superscript 1 each layer bends, stretches, rotates, and re-encodes the space. Training discovers transformations that make the classes easier to separate. One subtle correction, you said. Forwards and backwards pass are symmetrical mathematical relationships. They're related, but not symmetrical. Forward, input downward arrow prediction backward, loss downward arrow gradients. The backward pass is computing derivatives of the forward computation. Mathematically, it's applying the chain rule to the graph that the forward pass created. If I were building this from scratch, I'd first implement Rust matrix with Rust get set transpose matplotlib, then verify 1 2 3 4 times 5 6 17 39 works directly.
I didn't understand what I mean by symmetrical.
The fascinating thing is that once you have matrix multiplication and derivatives, the rest of the neural network is mostly repeated applications of those two ideas. The intelligence emerges because gradient descent continuously reshapes those projections until the geometry of the transformed space matches the structure hidden in the data.
When I say symmetrical, I mean in the same way that men and women are symmetrical. They're the two sides of the electromagnetic thing, which is the same thing, which is the electric field. So the forward and backward pass are basically encoding the relationship between gender on the thing, which is that relationship weights the movement, which encodes the geometry inside of the space. That's what's happening. But I don't want to code anything because I think that is gonna be... I don't really care about this example specifically. I'm trying to think about... And this is the annoying part about the inputs, is how to create something that goes beyond that. That's the problem. Because I think I'm forced to think about the inputs. Like for each input, you're gonna need a different type of shape, I think, because of the calculation. Because otherwise, like, how do you structure the shape of the matrix regardless of the input? You can make it generic based on the size, like the variables. Could be a generic thing. So maybe if I accept here on the new, I accept the size of the inputs as well. Maybe that's the way. I accept the size of the inputs and outputs, and then I make the rows and columns based on that, in order to make the dimensions of the matrix make sense. Then, like, the other thing that I'm thinking about, which is another obvious thing, is that the neural network has that calculation there on the microgrid, which basically all of them, as far as I know, uses, which is just the input times the weight plus the bias. But then obviously, why not use another mathematical equation? That's the other thing that I'm trying to think about. So I don't want to encode only that simple multiplication with the bias on the matrix. I want to create like a mathematical object that's able to calculate based on the input and output to train. I think that this is the thing. It has to be outside. So the matrix itself is only the weights. What encodes the relationship is the traversal. So it's how the values of the weights are going to be used by the inputs. And these two things are obviously connected. But the thing that I'm thinking is that it doesn't make sense to... I don't want to couple the matrix size with the input size because that limits the behavior, I think. Like, it's the same thing with the layers. Like, you should be able to tell how many layers you want. That gives you more flexibility and freedom. Because obviously, when you're thinking about optimization and memory, stuff like that, you want to be able to select how big you want the network to be. Now, obviously, it's going to impact results, but if I make it based on the input, it doesn't make sense. The question is, like, the first, what does it mean for the values, I think? It comes down to the function, I think. The weights, the values of the matrix are just the weights. I need to create like a function, obviously, of the backwards and forwards pass. But then the question is, how does it work? How do I determine the output here? Because for this case, obviously I could do this. And then I would get the same dimension of this one, and then I subtract and compare and then train like that. But I don't like that. I want to be able to do or whatever. So maybe I use D here. Maybe accept the... So maybe this I should be based... Not really sure if I can do this. just not sure I can do this. So it's basically complaining about not returning the output correctly, but so obviously the question here, I'm trying to see like if there's a way to do both of them at the same time. I think I need to study more like mathematics and concepts like that in order to think about this. Because obviously like the gradient is gonna be the derivative that is gonna allow you to get the rate of change, which determines the movement of the thing. But like why do you have to wait until the calculation is done there? Yeah, I think I'm gonna stop streaming. I wanna think more about this off stream. I need to spend a lot of time thinking about how to do this. I think that's pretty obvious to me, because obviously I don't want to do the same thing. Like I'm trying to do this from scratch to understand, like to think about new ways to do this that might make more sense. Based on the way that I'm thinking now, if I was gonna do the same as the other, like as the standard approach, I think what matters here is like this function here is about figuring out how to make this input shape work with the matrix shape, regardless of either one, to be able to create a mathematical equation that allows you to make the input interact with the shape of the matrix, which is a matrix of weights, which is the data, the values here. And then based on that mathematical equation, use the output to calculate the difference between the expected one. The output shape here that you get, I think, is the one that you compare against. So this would be the target. So you basically do like a simple equation, like the result would be like input shape, then like mathematical relationship, matrix. So this like is just the data and the rows and columns here. Then you would compare the result, like accuracy would be result minus the output shape, and you exponentiate so that negative values don't mess up the result. Then based on the accuracy, you do the backwards pass, and the backwards pass has to encode the mathematical relationship as well, so that you know based on the scope, based on the topology of the matrix, you know how the rate of change, how the topology should change relative to the local scope. Then you do this on a loop a bunch of times until you get a small, I think this would be loss, I think. So like as a small loss means you are close to predicting the output, then you have to be careful to not make it the same. So if this approach is 0, because then you are overfitting. So that means that the network is only going to be able to work for that use case and not generalize to other cases. Which is also something that's funny because it goes back to the whole thing about the whole purpose of this. The purpose of the network in theory, like not in theory, the practical purpose, like the way that it actually works, is to reconstruct the function, the original function, based on the data. But if you do that too well, then it loses the purpose, paradoxically, because the thing that makes it great is that it's possible that you can generalize that on the loss of information through the process of reconstruction. You gain the generality to make it work with other things. It's kind of like you are uncovering unknown behavior based on it's kind of like a scientific experiment. Yeah, based on the projection you're doing, which is the calculation of the weights of the network, you are discovering new behavior that you didn't know based on your initial assumptions. Your initial assumptions are the inputs and outputs. Then through the process of training, you are uncovering new relationships that you didn't know. I think that's the point of doing. But then obviously the question here is like, there's two questions that I have. One is like, how do I think about the mathematical relation, what the mathematical relationship should be to a generalized case? And the other one is whether or not you need to go back and forth instead of doing both at the same time. Because you already know the inputs and outputs in this case on this type of training. So couldn't you do both passes at the same time? Either at the same time or do it the other way around. Or there are multiple different ideas, I think. Like, one is to go from the output to the input. But I didn't think that would change anything. Then if you did the backwards pass, you can't really do it because you don't know the gradient. If you don't compare the result you get from the inputs, from the calculation from the input. So I'm gonna stop here. I'm gonna study more, and I think I'm gonna continue to do this some other time. Yeah, not really sure what I do think there's something like it is definitely becoming more clear to me how it works. But yeah, I think that the idea, what I'm gonna try to do is to build like a simple thing. To try to grow this on my own thing that I can use to train whatever network I want to have, and to study relationships, I think. I think I need to study more matrix, and like because a matrix is it can be viewed as a sequence of equations. There's a name for that I forgot. I think one of the names is Jacobian matrix, which is a matrix that has the gradients. I'm aware of that, but I'm not really sure if that's what I want to do here. Maybe this is like a good idea to do initially, but I think that this already exists. So like instead of having only one matrix, only one data here, I would have another one that is so like the original one. Yeah, but then here is not really it would be the weight, not the equation. Yeah, but I think that the idea of an existing one is that one You have one matrix that has encodes the mathematical equation for the forward pass, and then you have the other one that has the gradients, the derivative of that mathematical equation, and then you basically just multiply back and forth between the two. So I'm gonna stop here next time. I'm gonna see if I can study more, see if I can think about a different way or interesting things should do to run experiments based on matrix. And I'm not either I'm gonna do this next time or I'm just gonna go back to doing Rust training. So see you then.